Hello, I would like to talk about the importance of characterization while optimizing the manufacturing route of novel composite. In particular, I would like to talk about basalt reinforced composites. Basalt is a volcanic rock. When heated above 1400 degrees, it melts and it can be drawn into fibers. These fibers have 10 times the tensile strength of stainless steel. They have excellent corrosion and wear resistance. Their price is more comparable with glass fiber, however, their performance is more comparable to carbon fiber, and they have a density similar to aluminium. So let's see how we can make a metal matrix composite with basalt fibers and aluminium. But not with primary aluminium. We want to work with recycled aluminium. Why? Because 1 million tons of recycled aluminium leaves the EU every year, most of it coming from the UK. And it's a pity because if we were using recycled aluminium instead of primary aluminium, we would have a 95% reduction in greenhouse gases emission as well as a 95% energy saving. So why is it we don't use it? Well, the problems lies in the formation of iron silicide. In fact, recycled aluminium contains contamination of iron. This iron combines with silicon and forms needle-like iron silicide called beta phases. These are actually the cause for cracking, poor corrosion resistance, and poor formability. So what we want to try and do is actually put the basalt into the aluminium and see if we can improve on these factors. First of all, we need to optimize the manufacturing route in such a way as to avoid the problem of introduction of the fiber into the melt, to see what happens at the fiber interface and what are the reaction products there, to see if the fibers are wettable and what to do in case they are not, to avoid agglomeration in order to obtain uniform distribution, and to see if the density of the matrix and the fibers, if they differ too much and generate segregation. We need to avoid creation of porosity due to the fibers, and we also need to avoid anisotropic properties into the composite itself. In order to optimize all the condition and achieve better responses to the challenges just presented, we can do a chemical conditioning of the fibers themselves, changing their surface in such a way that they become wettable. Then we can physically condition the melt with the fibers in it in order to obtain homogeneous distribution. It can happen with steering, or it can happen with ultrasonication. And we can also, of course, optimize the casting itself. After a series of experiments, what you need to do is that you need to look into your material in order to see what's gone right and what's gone wrong, and then optimize the condition of the manufacturing again. So in this case, we can have a look here and see that what we are obtaining is a good distribution of the basalt fibers into the melt. Furthermore, those fibers are actually randomly oriented as well, so they are not gonna make an anisotropic effect into the melt. But more interestingly, when we look at the fibers themselves, what we can see is that there is a change in them. So instead of being having an homogeneous cross-section, what we're having is that we're having a rim of sort and a center. If we look a bit closer, we see that the center is still as it was before we started. So it's still amorphous, while the rim is actually grainy, so it's crystallized somehow. And around, we're actually having also phases that have a polyhedral shape here and even more visible down here. This is extremely interesting. So what are these phases? Well, these phases are actually iron silicide. But we say they were needle-like. Yeah, that's the beta phase. Also, we can have a polyhedral phase, which is an alpha phase. This is not detrimental. It doesn't obtain the same effect that the beta phase does. So this is a fantastic beneficial phase here. So we're trapping the iron around the fibers, forming beneficial phases. How is this happening? Well, what's happening is here. We can see the magnesium actually generating an initial nanocrystalline structure on the fiber. This is magnesium oxide, actually, nanocrystals. What they do is that they fundamentally create and free silicon. So we have an excess of silicon now that tends to go towards the outside, towards the boundary of our fiber. And there it attracts the iron towards the fiber itself, forming these beneficial phases. So this is a fantastic way to actually get rid of the iron and make it into a good item, the alpha phase. So that would be a very good way to use recycled aluminium and make it into an advanced composite. Thank you.